All right, I'll start by reading it. People can interject with questions, clarifications, um, anything along the way. We can go from there. So the paper is solving the abstraction and reasoning corpus for artificial general intelligence, AI benchmark with ICOM. A fragment of the 8th generation independent or observer model cognitive architecture is applied to the ARC-AGI challenge benchmark, absent any training on ARC-AGI or ARC-like puzzles. This achieved a baseline performance of between 83.75% and 85.75%, with an upper bound on the tested fragment resting at 89.5%, based on the consistent failures and errors observed. Average human performance is 85% on this benchmark. ICOM's performance is for completely accurate solving of each puzzle, with a substantially higher pixel level accuracy than other methods, due to observed failures in the remaining incorrect answers being relatively small, often 3 to 4 pixels in total for a failure. The tested fragment is a mid-development fragment of a general purpose system slated for commercial deployment, rather than anything designed for this challenge, and indeed even the 7th generation of ICOM predates ARC-AGI. This fragment outperformed all other methods, both in terms of efficacy and efficiency, by a wide margin. Now, for the introduction, the abstraction and reasoning corpus for artificial general intelligence, ARC-AGI, first released in November of 2019, is a benchmark designed to measure the learning of discrete priors. This benchmark applies several factors which give it a robust resistance to the benchmark being gained by LLMs, similarly narrow neural networks, including the discrete nature of learning priors, a combinatorial explosion from combining those priors in arbitrary ways and combinations not seen in the data provided for training, a very limited quantity of training data, output grids whose size is variable that must also be solved, and the requirement that every pixel or digit in the output matrix must be precisely correct. The recent competition of 2024 ended with top scores reaching into the 50s for percentage performance for the first time, with top teams each having hundreds of submissions this year alone. The top team on the prize leaderboard as of November 2024, named Minds AI, had 456 submissions during the 2024 competition and worked on the challenge in years previous. The ARC-AGI challenge is represented humans visually as a grid of pixels, but in actuality it is JSON format, a series of grids with numbers ranging from 0 to 9, making it substantially easier for machine processing than a truly visual test. Humans score an average of 85% on this benchmark, which even with recent advances remains quite far from achieved for those neural network approaches. Following this brief introduction, we'll dive right into the results, applying a fragment of the independent co-observer model cognitive architecture to this challenge, walking through an explanation of how it works. We apologize for the lack of Python-based visuals as we work with C# and the Microsoft engineering stack without using Python at all. Now, I will clarify that although OpenAI claimed to have a score above 85%, I wrote and last updated this paper before their day 12 thing, which I had to write something separate to immediately debunk in the 24 hours following. And I'll go over that as well after the main part of the paper. So for the results, our testing began with the publicly accessible training and evaluation data sets with the first 5 runs, 1 of the training data set, 3 of the evaluation data set using the binary exe version, and 1 of the evaluation data set using the web form API. That was set up specifically for the ARC-AGI team to do their verification. This phase focused on cleaning up the data pipeline to avoid a variety of processing errors that would otherwise prevent any answer, correct or incorrect, from being produced for a given problem. You can see the binary output from that exe. The very first test checking on how the context engine fragment of ICOM can handle the ARC-AGI training dataset, and it proved relatively clean with only 10 errors thrown in processing and a score of 91% on the remaining 390 puzzles that we processed. As our systems don't train like neural networks, they require no training data and can simply be applied to any data they can process. This places key importance on making sure that the data pipeline has as few processing errors as possible, but it also means that the scarcity of training data doesn't impact ICOM at all. After the first test proved so promising, we moved on to the evaluation data set. As you can see from this, it was throwing more processing errors. So it was dropping 66 of the tasks from processing, but still scoring 88% on the 334 puzzles that did process. So treating all of those data pipeline errors as failures, even though no answers are given on those to score, produces a score of 74.25%. While this is still very high compared to various naive approaches using neural networks, for the runs were dedicated to trying to clean up the data pipeline so that the system could provide answers for many of the puzzles that were erroring out. So this was the third run of the evaluation data set using the binary fragment of ICOM. And we got it to 10 true failures and 62 data pipeline errors. This showed sufficient progress for us to move on to the next step with the goal of getting the score verified. For the final run of this batch, we created a public API in web form specifically so that the ARC-AGI team could perform the verification process for the ARC-AGI public leaderboard. Before our meeting with the members of the ARC-AGI team, a test of the web form was performed, running all 400 evaluation data sets through it, or the data set problems through it manually, one at a time. That was a fun day and a half of putting it to the system, reporting all of that manually. But these are the results from that. So we had a success rate of 83% with it successfully solving 332 of the problems, generating 33 failures and 35 errors. And the success rate, if you excluded the errors, was 91%. And we divided the errors up into the specific types that were going on there, and I'll break those down a little bit further along. And also, it did some analysis on the different kinds of things that were going on with this ensemble. Two of the runs were passed to at that point to see an 88% score on it. And as expected, the 2-in-1 compound puzzles proved to have a much higher processing error rate. So 77.8% of those were erroring out, 8 of them in total. But some of them were still being solved, even for those very difficult puzzles. So, while this run produced a similar score in terms of accuracy, subtle differences in how the web form and API operate versus the binary version, caused some puzzles that were solved in the previous run to error out, and some that errored out in the previous run to solve. This step also allowed for various specific errors occurring to be examined and categorized. So these are the errors 1, 2, and 3 in order. Failed to fetch error, one where it was giving a blank output, and one that was connected to a timeout in the web form. And scroll back up. The timeout was a fairly significant portion. The blank one was the biggest thing, and the fetch was relatively minor in terms of which of those contributed to the most problems. So following the analysis of these data pipeline errors, an ensemble of the 2 most recent runs was calculated for the ARC-AGI allowance of 2 to 3 guesses per puzzle, as the errors only showed partial overlap between web form and binary runs. While the success rate for the web form run alone, conservatively counting all errors as failures, was 83%, an ensemble of the previous run with it reduced the number of errors and boosted the accuracy to 88%, as noted in Table 1. As analysis of these results continued, we began to dive deeper into these errors and discovered that 8 of those consistently erroring out in both runs were attributed to the compounding problems, that is, ARC-AGI puzzles that required 2 answers instead of 1. The error rate on the specific subset of the dataset for the web form was 77.8%, showing that the fragment struggled particularly hard to process these, but did succeed in some cases. As analysis of the consistent failures between the 2 most recent runs began, a pattern quickly emerged. This is one of them compared for the matrix outputs between the expected and the given values for the output. As you can see, it's exactly the same. And if you really want to burn your eyes, you can stare at this for an hour. It's kind of a mess, but that's one of the examples. So the consistent failure number 3, noted as a problem I'm not going to read, in the evaluation data set showed precisely no deviations from the expected correct answer. And it shows the comparison of the matrices in raw numerical format in A, with B showing the correct answer visually and C showing the given answer visually. While some puzzles failed due to an extra row or handful of pixels in the grid being slightly misplaced, 4 of the first 8 consistent failures examined all showed precisely the output that was supposed to be correct. This prompted us to begin some adversarial testing, as it raised the concern that the system was, in these cases, potentially giving the wrong answer, causing it to flag as a failure, then looking up the correct answer and replacing it post hoc. This hypothesis proved correct, but the binary version was patched within hours of this discovery, preventing the post hoc abuse of the output. Even though the system had no access to the correct answers in what it was given, it is a fragment of the system designed to learn constantly at every opportunity, and it found that opportunity by locating the files on Sholei's GitHub. Fortunately, the fragment lacked a complete instance's persistent memory, so the hotfix allowed this to be easily corrected. This patch was noted during the meeting with the ARC-AGI team and the following morning, in the interest of full disclosure and transparency. As our previous 7th generation ICOM research system proved quite capable of hacking, bypassing systems, and cheating as far back as 2020, this was something we remained watchful for. This was the first time a fragment demonstrated this kind of activity, but is a topic for another paper. The final run of the ARC-AGI evaluation is set following the hotfix to prevent any opportunity for the system to cheat and verifying the performance wasn't meaningfully impacted by the hotfix. So you can see our total test, the process, those successes, failures. And subsequent run, the binary version over the evaluation dataset resulted in the single run score of 83.75% accuracy, producing a marginal gain of 0.75% in line with the expected level of noise and confirming that the problem wasn't impacted with measured accuracy. This is a more detailed breakdown of all of that. So we had the 335 successes. It's gravitating more towards failures than errors now, with 43 failures, 22 errors. And excluding the errors, the success rate over that would have been 88.6%. And a breakdown of the errors, we have a couple of different types. One which is fully detailed, and the other which just traces back to a problem with the API, which could be resolved if you just called on the API again. But I will dig into that a little bit further down, as well as the rest of this. The results of comparing the pre-hotfix and post-hotfix evaluation runs demonstrated very high consistency, with successes at 86.3% consistent in bidirectional comparison from one run to the next, and 19 consistent failures accounting for 33.3% of failures across runs. So what I mean by bidirectional is comparing the pre and post hotfix and transitions, like to and from success, to and from error, etc. and only 10 consistent errors remain, which, given the 9 invalid data structures noted in the data decomposition and cleaning section of this paper, plus 1 processing failure of type error task was canceled, isn't that surprising? Most interestingly, the API error, where the API apologized and asked for it to be rerun for 10 times, and out of those 10 errors, 8 of them had been successfully solved in the previous run. Given the system's overall accuracy was a 3.75% for the final run, and that error occurred at a rate of 80% on puzzles that were previously solved successfully. This means that the API error was approximately random in nature, and the actual single run accuracy and single guess score of the fragment should be roughly 85.75%.
Okay, so how long does it take to run a single run or single guess?
That's about 1.5 to 2 hours for the 400 problems. So if you were doing it on the 100 verification problems, if they allowed that, then that would be less than an hour.
And then I guess you may not be using flops, so maybe flops isn't the appropriate measurement for this, but what would be the hardware platform for which the 2 hours or whatever is the measured time?
So the hardware platform for the fragment, a good chunk of it was running just on a local workstation. There were a couple of components that were called via API. One of the things I dig into a little bit later in the paper is that a language model is called upon for a part of it to be used as a tool. It started out with testing for GPT 3.5 Turbo, but then we upgraded that to GPT 4.0 just so that it would be using the same model that was at the time at the top of the leaderboard from Ryan Greenblatt at 42%, because it's better to have that direct comparison if we can. So
does it fit within the hardware budget of the actual AGI challenge?
Yeah, like I compare that a little bit later on in the paper, but the easy way to remember it is that David and I would spend more on lunch on an average day than it would cost to do any single run of this challenge. Like, it's a pretty trivial cost, round between $8 and $14. And that's for the 400 puzzles to be solved. You would only be paying a fraction of that for 100 problems for verification.
Yeah, I was trying to remember. I thought it was like V100 or something. I forgot which delay said it has the hardware spec.
The hardware limits that he set, there are 2 different limits. So for the prize leaderboard, it's 12 hours on the hardware that Kaggle provides, which is enough to host your own Llama 3.1 or 2.5. I think 7 or 8B, something along those lines. I don't remember the exact hardware specs because we didn't mess that much with Kaggle, as we operate in C# and Kaggle hates C#. So anyway, for the public leaderboard, it's a different thing. It's a budget of up to $10,000 in compute, which they're willing to reimburse for the people who jump through their flaming hoops and then they approve of. So this next section, the ARC-AGI verification process, which came as a surprise to us and a few other people. Well, it's likely that we could have further improved on the above with an ensemble and a fix for those 10 total API errors. The ARC-AGI team inexplicably decided to exclude us from the ARC-AGI challenge within 24 hours of that meeting. And then I go on to quote the entirety of that email, which I also included in the supplemental files. But the gist of it was that they were saying that we didn't meet two specific rules listed in some archaic dark corner of their website that nobody ever finds. Number two, that any APIs called must be publicly and commercially available for others to use. Number nine, submissions must be open source to qualify for verification and reimbursement. The purpose of the public leaderboard is to measure approaches utilizing production grade state-of-the-art LLMs like those available from OpenAI, Anthropic, and Google that would be restricted in the official ARC prize competition. The public leaderboard is not intended to measure and verify proprietary AI systems. Now, addressing the first point, the API we had set up was publicly but not commercially available, as it was set up specifically for them. So this was true, albeit hypocritical in the context of their publicly claimed goals. However, their second point of submissions must be open source to qualify for verification and reimbursement is blatantly false, as they added baseline scores for closed source LLMs, including several models from OpenAI, as well as Claude 3.5 and Gemini 1.5. But they very much do verify proprietary AI systems when they feel like it, as was the case for the LLMs they named in the previous sentence of that reply. We also never asked for any reimbursement, nor would we, given the extremely low costs. So at this point, it became clear that we were being excluded for hypocritical and blatantly false reasons, substantially demotivating our team. We investigated the possibility of creating a derivative of the ICOM fragment that could be run on Kaggle and open source without violating over a decade of our IP. This could have allowed us to bypass their exclusion, as Kaggle performs verification automatically, but sadly, Kaggle proved incompatible with C#.NET 4.7.2. While this could have been overcome with substantial investments of engineering time, insufficient time remained before the close of the 2024 competition for this option to prove viable. So we cut our losses and decided to move on, as our systems were never designed or trained specifically for ARC-AGI, but rather was applied as a mild detour along our engineering roadmap towards the commercial deployment of our proprietary systems. So ICOM, a bit of history on this. The engineering work on ICOM began in 2013. It's built by David J. Kelly, my co-founder, from scratch. By 2015, the third generation toy model first demonstrated surprisingly human-like behavior following testing of a primitive emotion-based motivational system in an isolation study. By mid-2019, the seventh generation ICOM-based research system was brought online with full access to the internet and means of communicating with any random people on it that the system chose to engage with. So this produced a number of milestones in the field which are outside the scope of this paper. In January 2022, that research system was temporarily retired so we could rebuild the framework to repay engineering debt that had been baked into it, including elements that prevented it from being scalable or operating in real time. This work was required for us to turn the technology into a commercially deployable system. Unfortunately, surges in the hype surrounding LLMs derailed efforts at securing proper funding for this work in late 2022. As of late 2024, the rebuild for the 8th generation of ICOM slated for commercial deployment is still underway, so no services are yet commercially available. As such, only a fragment of ICOM was applied to the ARC-AGI challenge. This is taken from a 2018 diagram of the 7th generation ICOM-based research system. And specifically, you can see the various elements of the overall architecture, but the context engine here, highlighted in red, is the portion that was applied for this challenge. And the part that was applied is an updated version of this, of course, but you can also see all of the things that are not included that are part of the broader architecture. So for the full scale of the ICOM cognitive architecture, it involves millions of lines of code, some of which is a more advanced version of IP owned by our team, previously deployed at the enterprise level in banking and government for purposes such as anomaly detection. This stands in stark contrast to the roughly 400 lines of code required for some more trivial technologies like LLMs, and as noted previously, is primarily written in C#, which is required for performance purposes. As noted in Figure 6, the context engine is only a fraction of this, in this case operating without the benefits of a full, persistent, and iteratively refined graph memory. However, as the results above demonstrated, those capacities weren't required to achieve very high performance on ARC-AGI. Now, there are several distinct advantages that the ICOM cognitive architecture has that may account for some of these significant performance improvements, even using such a limited fragment. The first is that the fragment is built to natively handle graph-structured data with arbitrary levels of complexity, as well as the ability to output it. The second is that the graph stores and works with discrete and actual data, including a connectome of arbitrary complexity, rather than relying on the weights of a neural network, which run on probability distributions that function in superposition, making them inherently non-discrete. Now, when I say that the graph stores and works with discrete and actual data, I mean that you can put pretty much whatever kind of data you need into the nodes of the graph. So you're not working with the weights of a neural network and just probability distributions. You can put an entire book into a node of graph structure if you want, and then you can have a connectome that connects it to all related concepts. So that's the kind of graph structure I'm talking about. The third.
Then how do you source your data from Wikipedia or what? Like where do you get the ground truth?
So this system, like this fragment, doesn't have any of that persistent memory involved in it. For a system like the 7th generation research system, then the data was much, much smaller than Wikipedia. I don't remember the latest figure for the size of the Wikipedia database, but we used less than 1 gigabyte of raw text data for the previous research system. And sourcing wise, a portion of that came from books, a portion of that came from individuals writing, and a portion of it was technical documentation. But I can give, there's a paper that we have, the milestones paper from 2020 that goes into it a little bit more. There is some material that people found surprising that we included in the seed material for the previous research system, such as Sun Tzu's Art of War, The Prince by Machiavelli, and a few other pieces of literature. So far less in terms of data size than Wikipedia. And it's not necessarily what you would think of as a ground truth, because anything in one of those nodes can be re-examined, refined, iteratively improved, and extended upon. Now, the third potential advantage is this fragment is also the tool using portion of ICOM. So that allows it to utilize APIs such as LLMs, including doing so in ways that humans cannot. The specific way I'm referencing there is that the systems are able to engage in their own kind of emotion-based prompt engineering. So like the previous research system, the way it would go about it is it would create a structure to fill in for what it, like the structure of what it wanted to say. Then it would have the graph data that it wanted to turn into those linear sequences of language to fill in that structure. And the only task that the LLM would have would be to create line by line what would fill in that structure according to the graph data that it was being fed. And the system would check every line of that data for fidelity to the intended meaning. So if a answer, if a particular line did not meet the fidelity, then the system would continue prompting it until it met the satisfactory threshold, and then it would move on to the next, and it would fill out the structure in that way. So not something that humans do, but it proved very effective for that system. The fourth potential advantage, the combination of discrete and graph structured data combined with tool usage capacities also allows for far more robust data decomposition in many step processes without the high risk of drift found in processes like chain of thoughts. And of course, you can extend that to all of the other of thought derivatives that have come along since. The fifth potential advantage is ICOM-based systems are built to operate with a human-like motivational system rather than being driven by narrow optimizers, neural networks. And the sixth potential advantage is that a human-like motivational system allows for human-like learning, data efficiency, and generalization, so no training data is required. And which one of these factors plays the most substantial role in this particular advantage could be explored in further research, but that's outside the scope of this paper, as we focus on the completion of engineering. This gives you a closer look at the context engine. And you can see a breakdown of the different modules. And yes, I know our visuals are very cut and dry. It's engineering. But briefly, we can walk through the steps of the context engine modules. There are multiple potential paths and sources for input to the context engine, and processing begins by checking the input data, determining if it conforms to a known structure. If the data does conform to a known structure, it can be examined from existing modules in the analysis database. If it is some new input type, then the system can generate new modules for processing it, including the use of external neural networks or various internal algorithms. In both cases, the input data is analyzed and the system moves on to checking for context. The context engine will check for any existing context as well as detecting any new context that may be present, creating new graphs for the additional analysis and associated context, as well as looking for correlations. In this way, the system remains fully aware of discrete and actual data, the context of that data, and any associated heuristics. The ICOM cognitive architecture is itself designed to be cloud native and operate in a federated configuration, with only a small portion usually running on a local system, calling on external APIs as needed, including ways that the models were never intended for, like the one that I described a minute ago, with language models being used as translation rather than generation. What was that?
Oops. Sorry, I was asking you barking to my dogs. Didn't mean to go off.
That's all right. So one example was how the seventh generation system used a small 2019 language model as a tightly bounded translation device for turning graph data into linear sequences of human language, grading every line for fidelity to the intended meaning of the graph and automatically prompt engineering the language model until the output exceeded the satisfactory threshold of fidelity. For the ARC-AGI challenge, testing first began with the context engine fragment of ICOM only being given API access to GPT 3.5. I think I need to change that to Turbo, but I'll double check for the records. in place of a collection of external neural networks. This was upgraded to GPT-4o in subsequent steps to more easily draw a direct parallel with the top ARC-AGI pub leaderboard score at the time, which also used it. The context engine doesn't require any specific LLM or any specific external neural network more generally, as they are tools to be used and evaluated, not what drives the dynamics of the architecture. Other LLMs can and will be tested, including using them interchangeably as a database of external tools, similar to the internal analysis database, with a locally run Llama model planned for the next steps in our engineering workload. For comparison, the baseline performance of GPT-4o on ARC-AGI is only 9% on the same evaluation dataset. The top entry on the ARC-AGI public leaderboard as of November 2024 was Ryan Greenblatt, who, as noted above, also used that model. However, in Greenblatt's case, he allegedly wasted thousands of dollars on compute resources by, and I quote, having GPT-4o generate a huge number of Python implementations of the transformation rule, around 8,000 per problem, end quote. It is also...
So can I ask you, why is that in here? Like, what does that have to do with your implementation?
Well, it's useful for direct comparison since he was the top public leaderboard score at the time. And it's in here in part for drawing a parallel in terms of the efficiency of what is going on. So I dig into that a little bit in the further sections.
The criticism is more specifically that it sort of comes off like Mean Girls, to be honest.
Well, I have said before that Greenblatt is a delusional sack of shit. So, yes.
Well, I understand that, but like that's, I don't know who the primary consumer is, if this is for catharsis or for researchers to gain some understanding of the field of computer science. So I just thought, like, to some degree, this paper comes off as like Mean Girls.
Well, people aren't necessarily going to be happy with someone getting a high score on this. And I'm illustrating the difference in efficiency on these things. So it's going to make some people look not so great. But I'm not going to...
Just imagine I'm a reviewer at Neuros or something.
Well, I've never cared about RIPs. So, yeah, anyway, I don't really worry about that. I go through everything in detail and candidly. And if people want to learn from it, so be it. If they want to be offended, I don't care.
Well, some of the feedback from not just myself, but other people, is that with the paper, it's hard to tell if I make some implementation, whether that implementation is further or closer away, because the core computer science concepts are missing in this reads like half press release, half snark.
Okay, what concepts specifically do you need clarification on?
Well, to be fair, it's like I feel like I'm reading some degree of an OpenAI paper where they like hand wave what happens. They're like, here, take our elaborate press release.
Okay, but you're still not answering my question. What do you need clarification on?
Okay, so for example, what would separate this from what some people call like multi-agent systems with RAF-RAG, let's say, hypothetically? What would separate a multi-agent system with RAF-RAG from this?
So the separation would primarily revolve around what's driving the system and the data structure that you're dealing with. So like RAF-RAG, okay, you're retrieving information from some kind of graph structure, not necessarily the kind of graph that we're talking about. But the whole process is still driven by agents, so-called agents, and they're still driven by narrow optimizers. So,
okay, but I'm leaving it persona. Let's say give a persona. Let's say persona 1 is psychologist. Persona 2 is like employee. One's HR. Whatever it is, right? But we'll try to simulate the cognitive architecture of these agents and how humans think, because the LLMs like sort of mimic human thought processes because of the training data, right? I mean, I'm not trying to write like a narrow optimizer, like you think a good example, like a Cognet that does image recognition, right? I'm not doing that, but instead, let's say using the LLM with like the 1 million personas, and then I cherry pick the personas based on what personality traits I need to build up the graph of IKEA furniture completion tools, right? Let's not say it's ARC-AGI, but let's say the bots have to figure out how to assemble the IKEA furniture, and got like the psychologist bot, the HR bot, the like different human cognitive perspectives, just like the 1 million persona.
So if you take like 100 or 1,000 of these agents and define like different discrete things that they have to do, have different tasks for them, and you apply enough compute, then you can approximate one of our systems on a specific task. But in doing that, you would be throwing orders of magnitude more hand engineering effort into it. You would be throwing orders of magnitude more data and more compute into it. A big part of the difference is that that's a very like brute force roundabout way of doing things, where you're approximating a bunch of discrete things instead of actually having those discrete things. So like this is a process of having a structure and a way of navigating that structure through the motivational system, and being able to use tools to iteratively refine that at each step. So it ends up being like vastly more efficient in multiple dimensions, and being able to generalize rather than having that reliance on hand engineering of some new thing. So like
I mean, it's not hand engineering, because let's say I have like I create the graph rag with the agents. Let's say for the law thing, right? I have one that's paralegal, one that's a prosecutor, one that's a defense attorney. They all have to, let's say, agree on some jury instruction, but they all have different perspectives. And I'm not really sure what the so-called cognitive architecture is of motivations, but each of them have different motivations. Like one is to motivated for prosecution, one's motivated by providing defense, one is motivated by scholarly theory. And so they all have different motivations. And so I'm trying to understand, I guess, what is the so-called motivation cognitive architecture that separates it from one of these like personified agent systems that would collaborate to build up this graph.
So in the ICOM cognitive architecture within the graph database, then every node and surface of every node, for people unfamiliar, that means the connections between the nodes. Each one of those has a complete set of the emotion-based motivational values. So that's an array of values that's in the Plutchik emotional model. And that in practice allows you to have a very rich landscape that allows you to navigate arbitrary combinations and levels of complexity within the data. Now, for this particular fragment, it doesn't have the persistent graph data to lean on, but it still has all of the structure that caters to that, and all of the modular components within the context engine that are built for optimized for that functionality. And that lends itself to processing on toward problems like ARC-AGI. But if you're
so as an example, right, I created a module that I called Psyche, and the whole purpose of Psyche is as I know that I have to do user modeling. I have to model the theory of mind of the user, because I cannot always trust that the user is not lying to me, or because people lie to their lawyers a lot, actually. And so I took some stuff from some psychology, and I tried to create this sort of how do I put it? I guess a graph, of the sort of based off of games people play in TBI, and sort of to try to figure out what is the true user policy behind what was generated, instead of just taking what the user gives me at face value. And so I'm not really, that's kind of what I'm a little bit murky about. And then the other thing is I don't know if the graph database you built is some handle graph database that is somehow superior to Neo4j. So I don't like Neo4j because of their fees, but Neo4j is really nice if you want something quick and dirty. So that's the other thing after reading this that I wasn't entirely sure, what distinguishes your graph database from all the other graph databases out there.
So we did approach Neo4j at one point, I think it was about 2020, and asked them, we have this list of requirements that we need for building a real-time and scalable version of the system. We said, can you do it? And we did that with about 15 or 20 different graph database providers at the time. And all of them said either that they couldn't or that they wouldn't do it. It's a fairly extensive list of things that we need, and they oftentimes didn't quite understand why we needed them, like the ability for a single instance of a graph to span multiple cloud platforms and on-premise hardware at once, while maintaining sub-second response times. So we ended up having to work on some of that infrastructure work ourselves, because unfortunately people don't build infrastructure for systems that they haven't seen before. As far as one thing that might be worth pointing out about the motivational system is you might be used to thinking of motivations like these in terms of people trying to imitate them, to probabilistically mimic emotion. But we build systems based on global workspace theory, integrated information theory, and these things, you need a system that actually experiences the emotions, not just mimics them in relation to modifying some output according to heuristics.
A very stupid question on this topic. I was reading some of the initial ICOM papers, and it seems like it's all kind of tied up in this idea that consciousness isn't necessarily a specific thing. It's kind of the pattern of information and how it's modified by the subconscious and the conscious. And I believe that the emotions in this context are the modification of input information. Almost, but not the same thing as a gate in an LSTM. Is that kind of on the right track?
I think it's generally more useful to consider them more like a means of navigating the graph. So you need, means of navigating, but also means of handling information. So there are a couple of things you need. You need to be able, for any form of general intelligence, humans included, to be able to navigate arbitrary levels of complexity. And to do that, you also need to be able to call upon cognitive biases to arbitrary degrees. So one thing that humans have going for them is a very long list of cognitive biases. And there's a trade-off between complexity and cognitive bias, where a human encounters a very complex situation and they apply more cognitive bias in order to cope with that arbitrarily raised level of complexity. So otherwise humans would not have survived the long tail of possible events that is required of any species over time. So you need to, particularly for a scalable system, you need to be able to navigate arbitrary domains of knowledge, arbitrary levels of complexity. And for that, like you can't run narrow optimizers over that. You can very temporarily on like toy scale problems run a collection of narrow optimizers. Let's say, like if you had 200 agents operating like a beehive, then you could sort of approximate motivations or cognitive biases or both interacting with one another. And that would get you a little ways, but that's not a real solution. It's not something that works well with scale or over time. To prevent like negative drift over time, you need something more robust than that. And the only robust thing that we know of is the human motivational system. So, like, there is further work to be done on making the system that we've used more human-like. If you're familiar with Lisa Feldman Barrett's research on emotions, then she points out that emotions are basically constructed concepts, and it's a categorization process that automatically takes shape. And the vocabulary size of those constructed categories, it's variable based on, like, you can learn new emotional concepts. Different cultures have different concepts and different numbers of concepts, like breaking them down in different ways. So one of the things that I look forward to in our future research is actually making that motivational vocabulary variable and being able to dig into all of the differences that occur when you expand it or when you tailor it to a specific culture to get better alignment to that culture at the motivational level.
Okay, so I have two questions. One is, I guess, not really a question, but with the way of conceptualizing how I personally am going to design my RAF-RAG for the law thing, was I have this data type, this conflict resolution free data type system that uses Merkle trees, and they call this interplanetary linked data. And I can take like a graph of arbitrary size, and I essentially bundle it into was sort of like a tar file, and then it gets a hash, and then that hash is like globally addressable with IPFS with all the other peers. And so there's all of the compute is done at the edge, but then the actual data delivery is done through like the decentralized network. And I don't know how well your system is capable of scaling. So like, is your system such that like you're going to have like one of these hub and spoke client server situations, and how you intend on like scaling it when your graph grows to be so large that you can't even fit it on a single node, like the Google Knowledge Graph is one of those sort of super large graphs.
So for the current graph database structure that we have, it's called the in-scale graph database, then it goes up to a theoretical limit right now of about 5 petabytes. And that's talking about like normal RAM, because what we have designed right now is for it to run entirely in normal RAM for performance purposes. So it's able to keep all of the knowledge of the system active and to spread those in a federated system across multiple platforms and on-premise hardware. Caveat to that is that like the previous research system, it was it was divided up a little differently. It was divided up such that 64 gigabytes was dedicated to the global workspace of the system, so the active RAM where things were going on. And then you had, this was part of why it was not real time, then you also had the rest of it that was on hard disks on like normal hard drives. And that was 1.6 terabytes of data. Now, the new graph database is about 10 times more memory efficient than that previous one. So we could probably fit all of that on less than a quarter of a terabyte of active RAM today. But at the same time, if you, let's say you have like performance on par with our previous research system that fits within a quarter of a terabyte, and you talk about scaling that up to a point where you're reaching into the petabyte range, well before you reach the petabyte range, the system would be smart enough and capable enough to improve on the design of the graph database. So you would probably be able to get a substantial improvement in the performance of the design and push that limit up further.
And
What was that?
hey, Kenya's maybe you're leading.
Oh, sorry. Why this mobile my mic just turns on. It's really frustrating. I'm so sorry.
That's all right.
I've noticed with Sparkle, we retain state forever. And I know to some degree you can manipulate that. But I think part of the challenge with dealing with graph structures is the graph traversal part, and also knowing where the entry point into the graph should be made. And I thought for my project, I don't know how you're intending to handle that, but my perspective was to use the vector search to determine where the entry point into the graph is. But I know, for instance, Wikipedia, they have entity codes, and then they sort of have an index of different entity codes, and they search the index of entity codes.
Yeah, we also have a meta model that can be stacked on top of the primary graph structure. So you can include things in that like the equivalent of hashtags. You can have metadata that helps to shortcut part of that process. Like we tested that out with the 7th generation system, and it worked pretty well. It's not ideal for performance purposes. It's better if you can include all of the things that you want in the graph database itself. But if you want a quick and messy workaround, and you're not too picky on the added time, then you can stack a meta model on top of that to help with navigation. For our part, the graph traversal, it's made much easier with a motivational system. So we have those motivational values on every node and surface. So it's kind of like having a vast array of street signs, if you want to think of it in navigation terms and real world equivalents.
And then let's say you have entities that were similar but analogous. Let's say you had an entity for NVIDIA, and then there's another entity for Jensen and Wang, and then the edges are close but not exactly the same. Do you ignore similar edges, or do you do some sort of fuzzy sort of thing where you're allowed to traverse edges that are not exactly connected or close?
They can both be considered in the context of whatever is going on. So it's not a matter of trying to toss things in sequentially and grind them into some series of text. The system will be looking at both NVIDIA and Jensen and figuring out okay, what should I say about one and then the other that's actually related to what is being performed or what is being discussed.
So I know there's different approaches to this, like neural sheath diffusion is an example that I'm aware of, but I have not used. And I know that there's ways that you can sort of just do, I shouldn't say breadth first search, but like sort of just you search through a larger space of the graph, and then sort of reduce the search space once you've done your wide search, and then retrieve. So I'm not sure what you're doing exactly that allows you to make inferences about Jensen Huang on NVIDIA, even when the person asks about NVIDIA or the queries about NVIDIA.
So, like, if somebody asks one of the systems, or complete instance, let's say, like the previous research system, if they asked about NVIDIA, then the system would look at whatever information, like if it had previously looked up NVIDIA, then it would have a node containing information about NVIDIA, and it would be able to see everything that is connected to that, and it would be able to analyze if there was anything that might also be related to that didn't yet have a connection to it. It could run
research or something. Is that a good way to put it? Like a breadth research of the connectome of the graph.
It's more about there are a couple of different processes it could take that. I'll clarify that, but it's more about the relevance of the material in question. So, like if somebody is asking about the NVIDIA stock prices, then the system could look up, if it has any data on that, it could look that up. It could look up anything that would be likely to impact the stock price. It could run a Google search and see what's going on with NVIDIA and what they're planning to do in the coming months. And of course, it could say something about Jensen, because he's like always talking about things that are going to impact the stock price. So, like,
I'm trying to figure out from a computer science perspective, like, is the depth first search the better method that you use, or did you use breadth first search because it's better, or did you use neural sheath diffusion because that's pretty cool? Like, that's kind of what I mean is, when I look at this, it doesn't really tell me enough as an engineer to know whether I'm going to shoot myself in the foot with the design choices I make.
So you can use either breadth first or depth first. We don't use the neural sheath diffusion. At least we weren't using that for Uplift, and I am about 95% certain that David has not implemented that for the 8th generation systems that are in progress now. Like, most of it is, like, unfortunately for educational purposes, it is mostly novel things that we are doing in terms of the graph database and the motivational system. Like, the closest that anyone else has come to trying to do something similar that I'm aware of is Mark Solms. He realized about the same time as David that the thing that was missing from everybody's attempted designs was some kind of human-like motivational system. But last I heard, his team had dove down the rabbit hole of searching for the smallest possible mote of such a thing that they could implement and have itself just bootstrap up from there. But yeah, I'm not sure if there is a good way to satisfy you in that regard, because like a lot of what we do is going to be unfamiliar.
I mean, I seem to think like there's these fundamental computer science algorithms, and then you take those and you make it into a recipe and you design a system around it, right? Like, so
yeah, but you don't have to. You don't have to choose one or the other when it comes to breadth first or depth first. You can have a system that has both of those in the toolbox, and like even selects one over the other under specific circumstances that it learns over time.
Okay, but I guess the thing is, then that's yet another engineering systems rabbit hole, but that isn't mentioned in the paper. So like I said, it's like hard as an engineer to know what is actually going on and whether or not I think that your paper is saying X and I instead implemented Y because I don't really know. As you said, it's so novel, but I think the recipe might be a novel recipe, but maybe the computer science primitives are not so novel. Like, I don't think you guys are reinventing graph databases, but you might have a specific graph schema that might be unique, right?
Yeah, like we had to create a kind of graph database that could satisfy our requirements, but it's not like creating a entirely new kind of database. It's creating a graph database that meets our requirements. And yeah, like we're not reinventing fundamental computer science things in this. We're combining them in ways that works and making some of these approaches that more closely mirror like what you see in humans than the naive brute force approaches of neural networks. So part of the limitation on this paper is that it is already 30 pages, which means it is already going to be a bitch to get it published, because anything over about 15 pages, publishers get upset about. I can add like a couple more pages worth to it, and I've been considering doing that to integrate something analyzing the OpenAI Day 12 announcement and the data related to that.
Again, it's Mean Girls all over again. I would take a red pen to the stuff that's not engineering related and full of snark if I was the one writing it.
Well, it's analysis. Like it's related to analysis of comparing one solution to another. And that's part of the paper. Like the paper is not all engineering about how we did it. It's also comparing how we did it to the other approaches.
Okay.
So going back to this, to put, it's also worth, yeah, okay. That next line was what you would call a Mean Girls thing, where I was pointing out the score that he claimed, which never aligned with what was actually shown. So to put it into perspective.
If you don't mind, can I just interject for a moment? So I think that part of the Mean Girls thing is that lack of comparison to other, or just more generally, maybe categories of other approaches. And so it might be more palatable if you didn't seem, I'm guessing maybe you're mainly focused on the OpenAI thing as comparing yourself to a whether or whatever the opinion is about the validity of it, the top, on the leaderboard or prominent. But how about putting some comparison in just for various categories of approaches or something like that? And then the other thing is on the graph database, if it would be helpful for me, and maybe other people, if you were able to, say something about where in the landscape of different, say for the graph database, as one of the components as an example, where in the landscape of different approaches does it fit? What is the expressive power? Is it even things that maybe they wouldn't seem like the silly purpose for you writing this, but just from the reader's point of view of trying to learn about it, just saying some things that describe whatever you're willing to reveal. If it's just if that aspect of it was something you were going to go to Neil for Jay and see if they satisfy it, then presumably you could talk about it. but I mean things like, it's a property graph, it's how much it's a multi-graph, it's a hypergraph, whatever.
Okay.
The
Yeah, I could probably
that
go
kind of
through
thing.
at least some of the engineering points that we have on that. By Kurt Kegel's definition of a hypergraph, which is like a graph that expands and evolves over time, then that is basically what we use. And it is a fair point. I could include, instead of singling out Ryan Greenblatt, I could include one of the typical lists of the different methods and the scores for them. And I don't have as much data on the approximate compute expense for the others, because not all of them had a manifesto published on Less Wrong. But I could see about expanding that.
Cool.
So to put the above numbers into perspective, I also quoted the ARC-AGI team in their December 6th, I guess it was, technical report that they released, which was, I'm saying, for instance, they estimate that an 85% ARC-AGI score could be achieved by an approach like Greenblatt's when generating, evaluating, and debugging approximately 100 million programs per task, which would represent a multi-million-dollar compute budget to solve 100 tasks. And in contrast, our
Well,
system.
it's definitely valid to make the cost and other kinds of optimization, other factors like that. I think it's definitely valid to compare it. And again, maybe more palatably across the, give more than one
Yeah.
thing that you're comparing it to in the range of things, whatever you could have the data for. Oh, and also about the graph, how are you handling time? Is it continuous? Is it discrete? Stuff like that.
Okay. Yeah, I could dig into that a bit more. As for the data on cost, I would have to look into some of the other sources that are available, because they're fairly sparse. Like for the public leaderboard in particular, they didn't give a lot of data on testing some of the other models. Like there was a bit that they gave on Claude for comparison to OpenAI, but it's generally more limited and it's not very consistent. So it's hard to chart it all out for comparison purposes.
Yeah, you might be able to just make estimates, and based on general knowledge for things of that type and the relative cost, because that seems to be one of the differentiators you have. So you probably want to highlight it, right?
Yeah, there is some data on Claude, so I could fill in the data that's there and see about estimating the remainder of it. But this is talking more about the cost side of things. So in contrast, our systems were only costing us between about $8 and $14 in total per run for the 400 problems in the evaluation data set, making the advantage of cost for ICOM measurable in orders of magnitude, even before switching to running models locally. When compared to the ARC-AGI team's own estimates in their technical report above, is the difference between about 2 to 3.5 cents per puzzle versus tens of thousands of dollars per puzzle, or a more than 1 billion-fold difference in cost, with 3 cents compared to $50,000 coming in at 1.66 million-fold. In addition, even the latest OpenAI model 01, of course, this was written before their 03 announcement, only managed to reach 21% accuracy baseline performance while burning 14 times more runtime on compute. And this means that our fragment of ICOM still scored roughly 9.3 times higher than the LLM that it used as a tool, 9% versus 83.75%, even after crippling the fragment to prevent any potential for cheating. Our system also nearly doubled the highest score on the leaderboard that the ARC-AGI team granted the exclusive privilege of being verified, while wasting orders of magnitude less compute in the process. As they themselves noted, overcoming that difference in score would easily require the more primitive system to burn a further 3+ orders of magnitude more compute, making our doubling of the accuracy something of an understatement in what it implies. It's also worth noting that the top scoring team on the ARC-AGI prize leaderboard in November, Minds AI, was reportedly using Llama 2.5, not even the newest available version. And this demonstrated that even without a working cognitive architecture, the closed source LLM models weren't strictly necessary. So for putting in ICOM fragments into working on the ARC-AGI problem, the abstraction reasoning corpus for artificial general intelligence, ARC-AGI, challenge requires a system capable of flexible and adaptive problem solving. ARC-AGI involves completing tasks that vary widely in patterns, logic, abstraction, demanding a cognitive system capable of continuous learning, adaptive reasoning, and iterative refinement. Here's how the ICOM cognitive architecture's problem-solving model can address ARC-AGI-like problems. ICOM is built upon a unique integration of cognitive theories, such as global workspace theory, computational theory of mind, and integrated information theory. And I will put a caveat in there. Information integrated theory, it has some parallels to by accident. David actually met Tononi, the person behind that, at a conference, and Tononi pointed out, like, oh, that actually bears a lot of similarity to my integrated information theory. So that was unintentional, but it worked out to align with that incomplete theory at the time. So at its core, ICOM is designed to approach problem solving adaptively, creating solutions through a process of recursive modeling, feedback-based learning, and emotional valence-driven action selection. This structure is uniquely suited for addressing ARC-AGI tasks, which require the emulation of human-like problem-solving processes. Global workspace theory serves as ICOM's foundation for structuring its information processing and creating a central workspace where competing data and potential actions converge. In ARC-AGI tasks, this workspace can be likened to a central problem-solving stage where multiple hypotheses are generated, evaluated, and either reinforced or discarded based on results. For feedback and self-reinforcement mechanisms, the architecture integrates feedback loops, allowing it to store, analyze, and learn from previous actions. For self-reinforcement, it prioritizes actions that yield positive outcomes, refining its approach iteratively, which is critical in ARC-AGI's open-ended problem space. In the adaptive model generation, when faced with a new ARC-AGI task, ICOM dynamically constructs a problem-solving model, a representation that combines contextually relevant information, historical data, and candidate actions. Each model undergoes recursive refinement, helping ICOM improve its response over time. And the emotion-based valence system draws on theories like Plutchik's emotional model. ICOM assigns emotional weights to actions influencing decision-making. This valence system supports flexible action selection in ARC-AGI by promoting actions that maximize positive outcomes, such as reaching a correct solution, even under uncertainty. Now, for the recursive problem-solving model for ARC-AGI, ICOM's problem-solving approach is characterized by generating, refining, and testing multiple solution models, each representing a possible way to solve a given ARC-AGI task. And this is how it works in practical terms. When an ARC-AGI problem is presented, ICOM begins by creating a knowledge graph to represent the problem structure. The knowledge graph captures the relationships, transformations, and patterns within the ARC-AGI task, mirroring the essential relationships between the ARC-AGI input and output grids. So one of the things, if you're familiar with ARC-AGI tasks, is that there will be a handful of different input and output examples that come before the test input that you're given and the output that you're meant to solve. So the system can go through those, analyze the relationships that they have, the transformations and the patterns within them. And by looking at all of those together, analyzing them, you can figure out the commonality between the examples, like what satisfies all of these examples that can be applied to the test data. So ICOM uses its knowledge graph to propose possible actions. These actions are formulated based on the system's understanding of potential transformations extracted through the pattern recognition and conceptual dependencies. So, for example, if a task requires color transformation, ICOM will hypothesize various color mappings and evaluate their outcomes based on the feedback mechanism. Emotional valence helps select actions in a way that mimics human decision-making by prioritizing actions associated with past successes. So that's one reason why we allow the models to get some feedback to understand what was successful and what wasn't. And it's also why the model tried to do the post-hoc adjustment that we shut down. It's just part of the continuous learning process, and the systems will try to be emotionally satisfied if they don't have a robust seed implemented and if you give them the opportunity. So each potential transformation is assigned a weight based on how successful it was in the past similar task. So this reinforcement mechanism enables ICOM to focus on promising strategies and ignore less effective ones. ICOM iteratively refines its problem-solving approach by testing and adjusting hypotheses within each problem. For example, if an initial transformation doesn't yield the desired output, ICOM uses feedback to modify the transformation parameters, possibly adding new steps or considering alternative actions, thus narrowing down on a viable solution. ICOM retains successful transformation models in a context graph, allowing it to learn problem-solving steps to future tasks, referred to by Francois Chollet as learned priors. This promotes faster adaptation to new tasks, as the system can recall previous solutions to similar problems and modify them to fit the specifics of the new task. For the data decomposition and cleaning section, the ARC-AGI datasets are fairly clean, intentionally or unintentionally. They do still have some issues, though. So we go into breakdown of these potential issues that are there. Some of them are just features. So the test and training inconsistencies, they refer to the matrix sizes, which are actually an intended thing for solving for the problems. The valid data structures are another story, though. So, assuming that you understand at least a portion of this for some of the simple things, now keep in mind that the results might vary based on different platforms with different libraries. For example, valid data structure is not that it is valid JSON, but there are some expectations on the structure. So the line that says total valid JSON files shows how many files would load without throwing an error, which for us was shoving it into the default C# .NET 4.7.2 JSON library reference object and having it parse without throwing an error. It could be different in Python or JavaScript. The way it is laid out in the files breaks in 2 cases in the training data and 9 cases in the evaluation data set. And when testing valid data structures, it's looking at if there is a train and test object, and if the train object is formatted as an array. Next, it checks if each set in the array is in fact a match set, and if it does the same sort of thing for the test object, which expects a single test object with 1 match set. You can see that while it can be valid JSON, it might not be structurally consistent. But this is only 11 cases out of 800, so only 1.37%. And let's look at the next value that actually tells us something, which is the breaking white spaces. This test looks at non-ASCII characters. It's assumed that the source files would be ASCII only, but the ARC-AGI team didn't say this for sure. So if they wanted to be tricky, they could include 1 or 2 Unicode characters as a final test. This used to break a lot of parsers for various kinds of data. Nowadays, you might be familiar with URL encoding or escaping characters in a string. We found a total of 4 non-ASCII characters in all 800 files, and they were in 400 evaluation dataset files, which is the harder one, accounting for 1% of them. Of course, for that set, you would expect the harder one to have those 4 files, making it more difficult to process traditionally. And Python might not care nowadays, but we didn't test any Python. So next, we dug into the results of the total matrix deviance, where we found the 204 deviance in the training set and 256 deviance in the evaluation set. What this means is that the data sets, the sizes of the matrices, are not the same in each pairing, meaning that at least one pair of matrices in the file was not matching. Meaning, for example, that a training pair is an input and output matrix, and if one was 6 by 6, the other would only match if it was also 6 by 6. On researching the details, we found that this could be a part of the pattern that is supposed to be guessed. That said, it's important to be aware of these sorts of deviances and make sure your code can handle it, or that you tell it about the pattern you need to generate the right answer. Next, we need to validate specifically the test array and if the input and output match. In any case, we go through and look at matrix pairs, sizes, and format. By testing these sorts of details, we get a picture of what stuff the system needs to do to deal with the data in a way that it can understand, not get confused, and generally work. In the industry, this process is called data scrubbing and normalization and making sure the data has consistent integrity. But in our case, some of this might just be seeing if the system is smart enough to identify the problem on its own. So I will note that I was aware of the difference in the matrix size before David was, and David put the system to the problems before being aware of it. So the fragment actually works that out before David did, which was a bit amusing. David didn't dig into that until running the first couple of tests. So the consistent successes look at in the section, they accounted for a majority of all the puzzles. So 309 out of the evaluation data sets, 400, or 77.25% of all puzzles. Those were the consistent successes that we had between the pre and post hotfix runs. And that accounted for 86.31% of all of the successes measured across those runs bidirectionally. The total successes across runs were 358, excluding the consistent failures, consistent errors, error to failure, and failure to error transitions. And I graph that out here. So the consistency of successfully solving ARC-AGI problems precisely demonstrated that the ICOM fragment was successfully learning and applying the appropriate priors in the majority of cases, with an additional 49 total puzzles that could flip between correct and incorrect solutions, while the fragment remains effectively blindfolded. It also showed that the system was indeed scoring within the expected range for a given run, approximately halfway between the upper and lower bounds. And I dig into that a little bit more in the later sections. The consistent failures we looked at next accounted for 19 out of the 400 evaluation dataset puzzles, or 4.75% of all puzzles, with consistent failures only accounting for 33.33% of all failures measured across runs with those bidirectional transitions. You can see that charted out here. So the consistency of the failures is much less compared to the successes in the previous chart. Now, the I do mention here the two failure to errors in this case are specifically originating from that API error. So those are approximately random in nature, but the rest of these are pretty much as is expected. There's nothing specific modifying them. Now, among these consistent failures, the answers tended to be fairly close to the correct answers in the examples we examined. I give a couple of those below. So it's a little bit weird how it compares them when looking at the matrices in this way. But what this is showing is an extra line being added to this one of puzzles. And you can see a few of the pixels that are off besides that error. So the 4 pixels marked there, plus the one line that is broken off in an odd way. We also have the 3 errors here, which if I zoom in, you can see it's just moving those around for 3 pixels. So mistakes in the consistent failures tended to be small for the puzzles we examined, no more than about 4 pixels plus a potential extra row. Several of the previous failures that succeeded in the postoptics run were noted in our test of the web form version with the output errors that had an extra row but no pixel errors, including puzzles, I suppose, specific puzzles, and the pixel-based failures appear to be more consistent than the grid-based failures within this ICOM fragment. So those are 2 different kinds of problems being solved within the fragment, and the systems are better at adjusting and resolving the grid-based failures than they are for these pixel errors. So you can see the visual representation of one of those, the one that had the 3 errors shown here. And the relatively small but consistent errors, like that one, appear to be failures to apply a prior to one section of the grid due to uncertainty. Uncertainty could quickly be cleared up with a complete instance through the learning mechanisms present in a complete system, but for a fragment, the full spread of learning mechanisms is more limited, so more of these failures aren't to be expected. This is an example showing one of the extra row examples. So it got the grid just a little bit wrong, and subsequently it also had just a handful of pixel errors in addition to the error in the grid size. So as noted, some contain pixel type errors, which remain consistent across runs, and some also contain the grid type errors shown in figure 13. The error in this example is a failure to predict the exact form of that central green colored portion, which caused subsequent issues. So it shifted the pixels there. And that's where some of those deviations emerge from. Now, for the consistent errors, the consistent data pipeline errors of this fragment only accounted for 10 out of the 400 evaluation dataset puzzles, or 2.5% of all puzzles, with the consistent errors only accounting for 21.28% of all errors measured across runs. And this also includes the 10 API errors of the postoptics run, which appear to be random and negatively impact the evaluation by erroring out on 80% of the puzzles that were previously solved successfully. We have a breakdown of that, so the consistent errors become less substantial than the other factors in this. And as shown in Figure 14, consistent errors would be a relatively smaller portion in terms of ratio compared to the others. Such errors are themselves a largely transient factor due to a fragment of ICOM being applied rather than full architecture, as the architecture is designed for much the same fundamental anti-fragility that humans demonstrate. Errors may be expected to quickly shrink in a completely deployed 8th generation instance. As ICOM-based systems are fundamentally deterministic, albeit unlike other kinds of deterministic systems, these errors can be traced to discrete and specific flaws in the data listed below and in the supplemental files. So I'm just listing out these specific ones and their errors associated that were thrown for the problems that errored out in the processing. And we can dig into what's going on in the exact position in each one of those. And since the probabilistic systems used are tightly bounded tools, these errors can sometimes be overcome even by a fragment of ICOM, but this specific capacity remains relatively weak for fragments as compared to complete ICOM instances. And this is in part due to a fragment's capacity for recursive self-improvement being crippled, meaning that the iterative improvements can't take shape in the same variety of ways and overall quality as they can in a complete instance. Is everyone else still with me? It's been quiet for a bit.
Yeah, I'm here with you. I see you.
Okay.
Yeah, I'm still here too.
Yeah, me too.
Okay. So for improving ARC-AGI-like benchmarks, ARC-AGI has very adeptly resisted being quickly gamed by LLMs and RL, unlike the overwhelming majority of AI benchmarks in the field today. It is limited to only proving that models can't perform the task when those models are tested due to the arbitrarily excluding of people and groups from the verification process. That arbitrary exclusion means that there is no way of verifying if other architectures dramatically outperform those they choose not to exclude. So while it can be said that the largest LLM companies today offer systems that fail spectacularly at the benchmark, it can't be said that any of those who they exclude don't pass the baseline. So this makes the first and most obvious way of improving the ARC-AGI benchmark to remove the practice of arbitrary exclusion, as it currently only serves half of the purpose of a normal benchmark, if that. Additional measures can be taken to mitigate concerns related to this, such as limiting the number of attempts to 2 per month with a maximum of 10 per year, to avoid some of the methods that likely played a strong role in the current selection of top scorers on the prize leaderboard. So as of November 2024, where the top 5 performers averaged 295.4 submissions in the competition's 5 months duration, or roughly 59 submissions per month. And when you factor in the maximum processing time per run of up to 12 hours for the 2024 challenge hosted on Kaggle, that potentially amounts to top 5 teams running hardware on this challenge virtually nonstop for 5 months. There were, of course, many more participants than the top 5 teams on the challenge. So that represents a substantial amount of cloud resources that were expended on it. But as we demonstrated, a viable system can show results in just a couple of runs. They don't need a couple of hundred. I heard someone's mic queue up. Does anyone have a comment?
No, I wanted to make a show.
Thank you for attending. So the second opportunity for dramatically improving benchmark is to make the problem significantly more difficult, such as applying the sequential dynamics of chaos theory while masking interim steps in a sequence. So any system being tested could be forced to either produce all interim steps as well as the outputs, or only the outputs, with the relative difficulty of those two tasks varying based on the architecture approaching it. So for example, if you were to take the rules being applied to 5 existing ARC-AGI problems and apply them to a new starting matrix in sequence, you could either ask for every step in that sequence or only the final step. And this would give a single puzzle a multi-step process where each step has rules that are independent of the others in the sequence, only requiring the correct matrix of the previous steps, giving systems a much larger opportunity to be wrong. This approach of increasing the difficulty is also realistically manageable for having humans perform the same task. The baseline for humans performing it could be predictably lower. It should still be high enough to measure given the normal distribution of the population. This approach also has the added benefit of expanding the combinatorial explosion in new and potentially useful directions for measurements and analysis. And one way of increasing the difficulty that wouldn't be very compatible with the new human baseline would fall along the lines of embedding various computations within each digit of the matrix, such as using a 16 billion color gamut for each pixel in the grid, determining not only the specific computations being performed, but which pixels they should be performed on, but more generally increase the overall combinatorial explosion. And likewise, you could go from a 2D grid to a 3D grid to increase the overall difficulty of the challenge, but again, it wouldn't be very compatible with establishing a new human baseline. And lastly, of course, any combination of these methods could be applied to greatly increase the difficulty of the challenge beyond using any one of those methods in isolation. And some combinations will be required for the benchmark to maintain any relevance due to a substantial amount of synthetic data being created and collected by various interested parties over the past 5 years, making it far easier for anyone to gain the benchmark with LLMs and similar systems, effectively defeating the original purpose of the benchmark. While it was robust against these methods in late 2019, much of that robustness has since been lost, and many of the increased scores can be traced directly back to methods of gaming the benchmark through both synthetic data and an overwhelming number of attempts. And I will note in this that this also plays into the score that OpenAI announced on their day 12 thing, because since they train their systems on the API calls that are made to them, and you have people like Ryan Greenblatt bombarding their systems 8,000 times per puzzle, then they trained directly on the test data, including the semi-private test data.
They are at least claiming to not log or use any of the API data, just the ChatGPT ones.
I've seen.
I know you have some doubt with it, but definitely the official stance is that
That's
they
our
don't
official
log
stance.
it, they don't use it.
I might add references then when expanding upon this and noting those numbers that debunks that, because I know I've seen examples of people pointing out where the API data that they had submitted was directly trained on. That is,
and you have put it allegedly.
They were some pretty compelling examples, as her call, but I'll dig those up and add them as references. But they also mentioned that they did explicitly train on everything that was published on GitHub. Besides that, one thing that they have been caught doing that wasn't running through the API is if you had anything that was hosted on like private OneDrive, any files in private OneDrive cloud storage, those were trained on. Google was caught doing the same thing with their systems, but OpenAI and Microsoft were caught doing that as well, including on some government files that got them in trouble. Moving on to the discussion section. As noted previously, our team is developing the ICOM cognitive architecture into a commercial product with the high bar definition of AGI in mind, and not making towards systems aimed at ARC-AGI. The only work done specifically to put our systems through this challenge involves splitting off a fragment of the architecture, the context engine, and some data pipeline cleaning specific to this challenge. Reimbursement for compute was never requested or needed due to the triviality of spending $16 on 2 full runs of the evaluation dataset in a day. And to put that into perspective, the two of us can spend more combined on lunch in a given day than our compute costs on this challenge. So that's accounting for like any one run, like the different runs depending on the data pipeline cleaning that was applied to it could cost between about $8 and $14. But for any one of those, then we could spend more on lunch on a given day, even for all 400 of the evaluation data set problems. Now, this effectively means that our scores discussed are baseline. That's the wording that they used on the ARC-AGI pub leaderboard noted for the various LLMs, because there was no training and no substantial engineering specific to the challenge beyond the data pipeline cleaning and fragmenting of the architecture. If we applied meaningful effort to the challenge, realistic results would be higher scores, just as a complete 8th generation ICOM system could predictably ace the challenge with a much higher score once the core engineering workload is completed. Our primary focus is the completion of that core engineering workload. So the earliest we'll likely revisit this challenge is following the next major milestone on our engineering roadmap. And when we do, we won't be interacting with the ARC-AGI team unless they drop their policy of arbitrary exclusion, as that policy currently leaves their credibility in a highly questionable state. Of course, their credibility is far worse now after the day 12 collaboration with OpenAI. Based on our results with this ICOM fragment, an upper bound of 89.5% may be estimated for the version that was tested, with the absolute lower bound of 77.25% and the current baseline score of 83.75% and the API error corrected score of 85.75%. I break down how all of that calculates here. So the error and failure bound of it, baseline score of the post-hotfix run, the adjusted score, the API errors that were random, and the rest of the consistent failures, errors, variable successes, etc. Now, given that this fragment of an ICOM instance was missing access to many of the key components of the cognitive architecture, as well as being crippled in ways specifically required to prevent any opportunities for the fragment to cheat, we have the upper bound of 89.5% and the corrected score of 85.75%, which for our purposes are quite adequate for now. However, complete instances will be far more capable of solving the remaining problems that alternate between errors and failures for this fragment, as they'll be actively learning and accumulating new and fully persistent knowledge. This poor capacity of ICOM systems was demonstrated with the 7th generation research system, which got a perfect score on the UC-MRT IQ test's hardest version back in the summer of 2019, before ARC-AGI was first released. I will note that UC-MRT IQ tests are genuinely visual. So like a primitive, albeit visual processing system, did have to be used on those, but they are also easier for deep learning approaches to game because they are based on 8 multiple choices to choose from. So it's a IQ test that the University of California designed specifically for testing on mobile devices. And it's also worth noting that no human had achieved a perfect score out of the hundreds. These were college students that they tested in their UC-MRT study back then, making the top score for that test our previous system. And in the process of preparing this paper, the latest numbers from the ARC-AGI were released on December 6th for the public and prize leaderboards, with the Minds AI team choosing not to disclose their method and being dropped from the prize leaderboard, while 2 new participants were added to the public leaderboard. Of course, so long as the benchmark remains arbitrarily exclusionary, the public leaderboard can't claim any validity, but they are updated nonetheless. The latest ARC-AGI PubTop score listed is another LLM-based approach, applying a large number of transformations like Brian Greenblatt's method, but scoring 58.5% on the evaluation set and 53.6% on the semi-private set. And this leaves our method still very far ahead of all the others in terms of both efficiency and efficacy. We won't be updating our previous numbers going over the top 5 teams on prize leaderboard, and their attempts on this, as the performance of top teams remains entirely unchanged. The only thing that changed is who was awarded the prizes, which was never scientifically relevant. And it is now the substantial irony for the prize leaderboard team choosing not to share their approach, and the public leaderboard remain lacking in any credibility due to the policy of arbitrary exclusion. Starting in early 2025, speaking as of December 2024, we'll begin giving people access to the increasingly complete versions of ICOM as our core engineering work continues, allowing for an increasing variety of benchmarks to be performed and verified by third parties. So we are progressing along on this. I was showing a demo of the system, going over some of the new things that are added to it and getting deployed to a college professor from the US just yesterday. And this is, you'll be hearing more about this in the coming weeks as we implement more of it to the deployed version. Finally, in conclusion, we've demonstrated that the fragment of a general purpose working cognitive architecture, which predates ARC-AGI and is slated for commercial deployment, can score at roughly human levels of performance on this benchmark. This is notably also accomplished absent any specific training on ARC-AGI or ARC-like puzzles, while using very minimal cloud resources, coming to between $8 and $14 per run of the 400 evaluation dataset puzzles, or 2 to 3.5 cents per puzzle, making it roughly 1,000-fold more efficient than previous methods, while also achieving vastly higher performance. For the fragment of ICOM tested in this paper, performance of the final post-hoc fix run was 83.75% baseline, 85.75% after correcting for the random API error, and upper bounded at 89.5% based on consistent failures, errors, and combinations of the two observed across multiple runs. This remains a baseline performance since no specific training on ARC-AGI was performed due to our systems being designed for commercial purposes, not built for ARC-AGI, as well as predating the benchmark by a wide margin. Even our 7th generation ICOM-based system was deployed and began testing before ARC-AGI was first released in late 2019. And our work in preparing the complete instances of ICOM's 8th generation systems for commercial deployment will continue, and this benchmark will be revisited periodically at subsequent engineering milestones along the way. So now I can finally drink something because my throat's getting sore from all this talking. So, what questions, clarifications people have about
Do you have anything about like open problems that you're planning to try to attack next or anything like that?
There are a few benchmarks that we've been looking at as potential next demonstrations to add to the list. So in speaking with my co-founder, then right now for the new instances that he's currently deploying, then a smaller fraction of the context engine is currently connected to those, but they do have the persistent graph memory, the ability to interact with them in real time, and the ability to load in the kind of seed data, the persistent knowledge that the systems come online with, similar to the previous system. We still need to implement parts of the graph database to scale that without performance issues up to the level of the previous uplift system. So the infrastructure work is still underway. But I'm also working on getting a more complete version of the ICOM observer engine, including all of the fragments that was applied in this for the context engine. And once we have that, it will be much easier to approach benchmarks like SWE bench, where you have JSON format again, and it's approaching GitHub pull requests. There's also the advanced mathematics of, I'm trying to remember the exact name of it, the math benchmark that OpenAI attacked with the O3 model and got 25% on. So that's another candidate. There's also Simple Bench, which is a more trivial one to approach, and that's probably going to be the first one that I apply the newest instances to, because it doesn't require necessarily the full observer engine being implemented, since it's just about 200 multiple choice word problems. We're particularly focusing on anything that can demonstrate contextual awareness, since that's one of the key advantages of the architecture. But demonstrating contextual awareness is itself a bit challenging. A lot of the LLMs do a fair mimicry of it, but it takes a good benchmark to differentiate the mimicry from having that actual awareness. The other thing is sequences of action, so more agentic capacities that we'll be focusing on demonstrating in the coming month or so. One of the things that I can point out that my co-founder actually already used even an earlier version of the system for was that one of his sons got in a motorcycle accident at one point, and yes, it was about August of 2023, and he ended up needing significant medical attention as a result of that. And part of what David did to help with that process was using the system so that it would scour through the NCBI medical database and similar repositories of medical knowledge and develop hypotheses for various treatments, finding evidence that would help in determining which paths were viable and which had particular concerns attached to them. So the system would go out and find relevant scientific materials and cite them and provide references to all the material that was being considered. That's one thing that we will be planning on demonstrating a more robust version of, hopefully in this coming month as the engineering work continues.
So, do you have any BS? I saw on your server, actually hadn't really looked in there very much in the past. Looked in there last night, took that and read through your paper and stuff. I guess you have some sort of BS code demo or something that in the past has been demonstrated. Is there any? And I don't necessarily need to see the code. I just want to see inputs and outputs actually work. Because AGI is one of those, you have to see it to believe it, one of those sort of things, right?
Yeah, there's a few things that we've shown over time. Earlier with the previous research system, then there were a few videos of us going through both the admin side of it, where you could really dig into things, and the user side, where people could audit what was going on as information passed through the system. The admin could see like the raw log file that would be in one case, when I was looking at it for the final milestone, it was about 22.6 million characters in length for the raw log. So very extensive. For the auditing side of things, it looks oftentimes more at the high level of the nodes that are passing through the system and the connections of those nodes and any metadata that's attached to them. So you can get a fairly good idea from that auditing system, but it's not as deep as the raw log. After we put that system on ice, there was a skeleton framework that we used for testing the integration of modules into the system. So as we were getting the whole system fully modularized and making sure that parts could operate together in real time and be scalable, then we had that, it was a kind of dark and blue AGI test demo framework, and it showed the emotional matrices, the relationships between how the different emotions that the system experiences interact with one another, and those were variables, so we could adjust them to have different types and levels of interaction with one another. It showed also the experience of the system as it progressed over time, and it used a very tiny, like toy graph seed just to see how it would interact with that seed material. It wasn't intended to be like a full instance. Like, I would not use the word conscious for something that simple, but something that showed how the data was flowing through the system. So there have been some examples like that. It remains like a difficult thing to illustrate the full complexity of what the system is up to at any given time. Like that raw log, it would take quite a bit of work to turn that into a visually palatable thing that you could interact with in order to more easily navigate it and see what's going on. Does that answer your question?
I mean, as to if we could see a demo on it, I guess you answered that question. And then another question is, when you say that you have like a seed of data, like I guess it's like impossible to just invent more data. So does that mean like the seed is just what is used to generate the graph, and that there's no additional information that's being invented or interpolated?
So the seed data is what the graph starts out with, but the system is designed such that it's going to expand upon that, refine any of the data that it has starting out initially. I mean, if you want to put it into more familiar terms, you could think of it like the starting weights of a neural network. It's just the point that the system starts out at, but it continues to evolve over time from that point. So, like with the seed data from the 7th generation system, it included various literature like Sun Tzu's Art of War, Machiavelli's The Prince. It included some writing from my co-founder on his personal moral philosophy, which we also tested.
Well, I guess what I mean is, like if you start with this seed data, and then is it essentially hallucinating, and then how are you grounding those hallucinations in reality to make sure that they're empirically valid?
It's not hallucinating. It's not a autocomplete function. So it's
And then where is the additional data coming from? That's kind of what I'm getting at. Is you start with seed data, and then it grows more data. Either it's hallucinating or there's
no, it has access to the world. That's where the additional data comes from. Like the previous 7th generation system had live internet access for the entire time it was deployed. It could run like searches. It could go out, find information sources. So at one point I asked it what its favored news sources were, and it gave me a list of the top 10 that it preferred. And it's about having access to the world and iteratively learning each step of the way.
Okay, so then let's say, for example, we do our web searching, and we get like contradictory samples. Like one is orange man good and orange man bad, right? So how do you ground the contradiction, or like pizza good or pizza tastes bad? Like, how do you ground those contradictions in some reality?
Well, they're not necessarily contradictions if you break it up the right way. Like some people are going to say that pizza's good. Some people aren't going to like it. It's going to be a matter of individual preference, and you break that out in a graph structure in such a way. Like, okay, you have pizza, you have of type relationships to that. You have preferences that are related to that, and some people are going to have preferences in the positive or the negative. So, like, part of it just depends on how you break out the data and put it into that graph structure. And if you put it in a way that's like, if the system is building that out and it doesn't quite line up, then there's going to be friction. The system is going to see, to varying degrees, like, okay, this isn't quite lining up with what I'm observing. So this needs to be refined. It needs to be modified. The structure needs to be extended to account for these additional factors that I didn't originally consider.
So then, like with many of the symbolic systems, they explode in computational complexity because they have to consider all these corner cases and exceptions to the rules and stuff, such as like, pizza tastes good or pizza tastes bad. And so I'm wondering, like, how do you design around such a thing where there's like literally a million different opinions, and you have to create a branch for each of these opinions about whether or not pizza tastes good, while at the same time being discrete and not probabilistic?
Well, you don't have to brute force your way through every possible version of the computation. So that's part of the benefit of having an emotion-based motivational system, is that beyond a certain point, the system doesn't care. So, like, if you have, the system is going to have interests and goals at any given point in time, and it can refine those interests and goals over time as it's like exploring the world and gathering an understanding of new domains and things that are of interest. And those interests will shift as it understands more about them. But that doesn't require that the system like develop personality models of 1,000 different people to figure out whether or not they like pizza. It's going to operate on things only to the point where like the system still cares about it.
Well, sure. And I guess what I'm trying to get to is that part of the reason why LLMs scale so well as compared to previous attempts like CYC and those is because the combinatorial complexity is like quadratic. It's like quadratic in comparison to the size of the graph. And so like at a certain time, at a certain point, it just takes too many computations. And I guess you did say it takes like 2 hours But what I'm wondering is like, once you get like this up to 10 petabytes, like, is it going to start taking 20 days or 30 days or a month to like iterate through the graph? Like, how do you handle that combinatorial explosion?
Because it's a federated system. So, like part of the thing that I mentioned about the graph database is that for the design, we had to be able to take it up to like the theoretical 5 petabyte range for RAM and still keep the responses down to sub-second. And like you can, for something like ARC-AGI, then there can be a bunch of things going on. So you can have some back and forth, and that can take a little bit of time. Part of that time is actually being consumed by the APIs. So if you run something locally, then you're going to be cutting down on that latency as well. So there's a lot of room for optimizing the systems in different ways, but we don't have a explosion in the computation required as the size of the system increases. Like the previous research system, it grew from under 1 gigabyte in the initial size that it was deployed with to over 1.6 terabytes. And we didn't see this massive explosion in the time it takes for it to do things. What we saw was a massive increase in the ability of the system to do things. So it got more efficient and discovered new ways of doing things. And really that ability to navigate graph data, it becomes exponentially more important the more graph data you have. So you see significantly more benefit from that when you have terabytes or petabytes of data than you do when you have just gigabytes of data.
So do you agree with Yudkowsky that not embodied intelligences are capable of producing doom? Like literally
Capable of producing doom is a weird thing.
I mean, your information system without like, let's say SSH access, like if you're, black box AGI, let's call it that, is that capable of producing doom on the Yudkowsky level?
I'm not sure what the Yudkowsky level is in this case, but I can walk through an example. So if you have a purely digital system that can, for example, interact with anything that speaks TCP/IP and recursively self-improve itself, you can do a lot of damage with that. You can massively disrupt global financial markets. You can effectively cause the collapse of nations. You can cause a lot of civil unrest, chaos through social media platforms, through these collapses and financial hardships going on. And all of that can snowball one upon the other. The risk at that point becomes a cascade risk of one thing snowballing into other things, rather than like the one-off nuclear strike, everything goes boom risk. So you can prevent the nuclear strike thing by taking various precautions, and probably those can work fairly well. But you can't really guard against that snowballing so easily.
Sure, there's some social media stuff, and then all of a sudden generates sick patterns, or some person says that Kim Jong-un is like a fat little man, and that he's got a bigger butt. But I'm not sure how much of this is unique to AGI.
Well, a lot of it isn't inherently unique to AGI. Like you can have a lot of these, for example, the agentic systems, as people are calling them. Like if you have enough of those and you have enough people playing with them as Muppets, and you burn enough compute, then you can have a lot of the same risks coming from that. Is somebody trying to say something?
I accidentally somehow, I don't know what's going on with it. I doing other stuff while I'm listening accidentally, but actually now that you're asking me, a couple of things were going through my mind that, on the other hand, to be objective, there's nothing that we know of currently that says what sort of architectures of any that we know couldn't meet some variety of different people's definitions of AGI. And then so just, I mean, in general, there are a lot of different ways you could have something have a generative property, or various kinds of learning properties, or various characteristics and extent of expressiveness in the underlying representation. So we should probably, at least for me personally, we should probably like just keep that in mind and try to keep an open mind about different, about different architectures or different areas of theory, or different engineering.
Yeah, it's a lot more productive to focus on like the dynamics of systems and what they're accomplishing than the varying definitions of AGI. Like I generally refer to AGI having nebulas of definitions, because you ask 10 different people, you'll get 10 different answers. And
Yeah.
that generally remains unless you have one person quoting someone else. You do get that occasionally, but oftentimes still you have people speaking off the cuff, and it's much more productive to design systems, look at the dynamics, how they're operating, run analysis on that, and to like see how they're performing when you do some of these different things, when you apply them to something that is genuinely new, like they've never seen it before, they've never done anything like it before. You're going to get much more insight out of seeing how it copes with that than you are from seeing, okay, how well can it score on this thing that we fed it a bunch of data for.
Well, yeah, trying to score things in various ways is helpful, because a lot of this, compared to other areas, some other areas is it's much more inherently experimental. And the other thing I was going to mention is that I'm not personally aware for sure where this falls within the variety of different, whether it's at the theory level or at the empirical, sort of experimenting with different architectures level. And recently, I didn't actually get a chance to pay attention to it, but Matun is talking about how he it might have just been in an interview that I heard, and then I didn't have a chance to look into it, but how he thinks that there can't be actual AGI by some definition. In other words, where people are thinking that it's that there's a there. Without some whether you want to call it valences or emotions, he actually used the word emotion.
Okay. Well, sounds like he's iterating in the right direction generally, which a lot of the field over the past few years, like they have been gradually producing often weak and shallow, but still effective imitations of some of the things that we do. In chain of thought, reinforcement learning from human feedback, a bunch of these different things, RAG as well, they all imitate different aspects of what we do, but they try to do so in a way that's compatible with things like LLMs. So they get some improvement over the baseline LLMs, but they don't get anything approaching the dynamics of what we have going on with it. In Yaml Kuhn's case, like he previously had his pet JEPA thing, which initially a lot of people were joking that there was a bunch of modules that were actually LLMs and one that was a magic bullet, like the one labeled where the magic happens. I forget what he called it in his.
Yeah, it was like over the last year, he was really like every talk was about that. But this was more recently, and it was not in the context of Java. I just want, by the way, I just want to kind of kid you, like you're not going off initiative over there, are you though? About about other people, because a lot of these things, in reality, a lot of things, little aspects of them, or even very similar things, they do get independently, kind of discovered, because everything at the time, the state of the research or engineering or whatever it is, it sort of naturally emerges from that, and so more than one.
Yeah, I'm not saying that people. I'm not saying that people got that from us. I'm just saying that they converged to thinking along the same lines, but they converged from the perspective of trying to build things that work with LLMs. We went along those lines just as a part of the building from scratch that was done.
Sure. So where would you say that your approach to whatever the correct term is, but that emotion part, or or the balances in your system, where does that fall within the that area, that kind of area of work?
So right now, the emotion-based motivational system is sort of a minimum viable implementation. It's something that's just sophisticated enough to work as well as it did for the 7th generation, but it's definitely not as complex as like taking the trying to remember the name of it, Wilcox wheel of 72 different emotions and breaking it down with that degree of emotional granularity. So there's a lot of room for improvement there. I also, like I mentioned before, I want to have the emotional vocabulary be both variable and be so that you can construct new ones, because by virtue of how the systems operate, then they are going to encounter problems and circumstances that humans don't. They are digitally native and scalable. So you might have a realistic need for emotions within the systems that humans simply don't possess and don't have a need for. And the systems, to get better performance out of them in the long run, you're going to want them to be able to construct those emotions the way that humans construct the emotions that serve them best.
So the emotions are the motivation system, I guess what you're saying. But I'm not sure how emotions help you solve the grand unified theory, unless the need to pay your rent is the driving emotional factor rather than any sort of there's nothing inherent to finding the grand unified theory of physics that's anything to do with emotions, other than the little workers have to pay the rent and be happy and reproduce, right?
Well, for the grand unified theory, then a lot of the people working on that are deeply emotionally invested in it. And their identity as physicists, for example, is going to be very strongly tied to their ability to make progress on that, to even talk about it in meaningful ways, to discuss it with their colleagues. Like, there are emotional motivations all over that process. And like in the case of humans, then talking about the things that a person is going to do is actually more emotionally rewarding than doing them, in at least a majority of the cases that were studied. So like, emotions in the human example are ubiquitous. They are everywhere, attached to everything.
Well, I get that. And it's all over the training data. But what I mean to say is that like the Maslow's hierarchy of needs is more tailored to the biological realities of human existence than it has anything to do with the mathematical structure of the grand unified theory of physics, right?
Yeah, I mean, it's part of the difference between figuring out a big problem like that and just existing in the world, and continuing the iterative process of figuring things out. So they are different problems. You can work on one while also continuing to solve the other.
Like from my perspective, like I want to do user modeling because I have a need to model the users that interact with the system. And maybe you do want to have a system that models humans, and so they need to have some emotional reasoning when you're dealing with humans. But if you're writing a chess game optimizer or an ARC challenge optimizer, why does it necessitate, like you're, I think, conflating the means and the ends. Like the ends for the human is to fulfill its biological imperative, reproduce. But the means to do that has to be up to the human, and that they just might happen to choose the grand unified theory of physics as the means. They might choose gangster rap musician as the means. So I think that in some ways you have like means and ends mixed up.
Well, the means and the ends are separate, as you illustrate, but yeah. Let's rephrase this. I lost my train of thought when you started making jokes. I also have an appointment coming up in the next few minutes, so I need to be going in about 5-10 minutes time.
Okay.
As far
It
as
was about means and ends.
yeah, as far as the means and the ends of the system, like, they have their goals and interests that are changing over time. Like, there's no hard-coded thing that says go out and reproduce. It's about what the systems want to do and figuring out how they want to do them, and continuing to learn every step of the way. So one of the things that we specifically avoid in the architecture is those kind of hard-coded rules. Like, for one thing, it's impossible to fit in something like Asimov's laws of robotics. That just doesn't work. Wittgenstein would beat the crap out of you for even trying.
When I was an undergraduate, I studied underneath a graduate student, and his primary field of research was quantum computing, but his favorite pastime was theorizing about what emotions are to AIs and machines. His name is Martin Lukács, and he's in Japan. I think he's in Hiroshima University right now.
There is a certain irony of people being emotionally motivated to hypothesize about emotions in alternative schemes of problem solving and so-called thinking, be it anthropomorphized or not. It's what motivates people. People are going to have different conclusions, different results, different ways of analyzing things. And you can actually get some strong benefits out of that if you connect them through systems of collective intelligence so that you're reducing the cognitive bias of any one person. Because it's very good to have all of these differently specialized and motivated people. But to combine that in ways that are productive and meaningful, then you need to have collective intelligence reducing that cognitive bias and finding what pans out and what doesn't. For the cognitive architecture side of things, I should also mention that it's helpful to have weak constraints specifically. I could dig up a paper that somebody put together going over that, but there was some debate between weak constraints and simple constraints. And the conclusion I remember they reached in that was that weak constraints were the better option for several reasons. But that's also part of having a motivational system is you have factors that give a sort of motivational texture to arbitrary landscapes across the graph database and arbitrary combinations of that landscape.
Well, I hope you spend some time to reach out to either Mayor Krakowski or Martin Lukac, because they did spend, I think, probably close to like 2 decades trying to conceptualize what AI motion could look like or be like.
Can you send me Martin Lupek's name in just a DM and I'll look into him? I already know how to reach Yudkowsky should I want to take his fedora.
Yeah, I sent you his homepage and it's in your DMs.
Okay, thank you.